is Alexis Marceau.
And I'm Charles Laverdure, and today we're going to present you a quick video on how to measure displacement and especially strain using a DIC, digital image correlation.
Today, in this short educative video, we're gonna show you what is strain and explain to you how to measure it and what is the cause of strain. Then, we're gonna talk to you about a new optical technology, the digital image correlation. We're gonna first explain to you the working principle of that technology and then show you how the engineer, using their own camera and a computer, can measure displacement on any objects. Finally, we're gonna show you some of the different applications where the digital image correlation is used today to help the engineers and the scientists achieve their goals.
Okay, so in this first part we're going to talk about stress and strain using this little piece of foam. So sorry, but we're going to start with an equation. And this equation simply says that a stress is a force over an area. It can be either tensile, which is going to interest us with our piece of foam, or compressive. Let's apply a tensile stress to our piece of foam and see what happens. At the beginning of the experiment, our member has a length L, but by the end it got deformed and now has a new length of L plus the deformation delta L. And so, by just plotting delta L over L, you get the strain applied to the member. Deformations in the X and the Y direction are relating by the Poisson's ratio. To introduce you to the concept of the DIC, let's place a marker on our piece of foam. And now, let's pull the same tensile force. We're gonna see that before and after the force is applied, the marker moved by a certain distance. This distance is called displacement. Hey Alexei, got it?
Principle of working of the DIC is simple. It takes a first picture of the object and set coordinates to every little point of the object. In this case, it's the apple that it's at the coordinate 2 and 6. It then takes another picture of the object under some different condition like strain or heat, and it set other coordinates. So as you can see, the apple changed place. Then, using its pixel represented as the grid there, it can measure the difference between the two coordinates using simple equation showed right here, and it's how you get the measure of displacement using the IC.
Okay, so by calculating the number of pixels our reference points moved from, we get the displacement. And with the displacement, it's really easy to get the strain, because if you look at this equation, the displacement corresponds exactly to the delta L. So delta L over L is the strain. You get the strain by counting the number of pixels that your reference point moved.
It's also possible to get the stress applied on the object. Once you have the strain, you just get the constant of elasticity of the object, and using this equation, you can derive the stress applied on the object. With the stress, you can derive other parameters like the force applied on the object.
Okay, so to show some of the limitation of the DIC, we're gonna take a step back and make Alexei and his apple look really small. But we're gonna keep the exact same number of pixels as in this first experiment. Then, we're gonna ask Alexei to do the same movement. And you're gonna see that when Alexei is far and appears really small on this screen, the movement of the apple is not that heavy. Here we have a movement of only 1 pixel compared to 7 pixels in the previous experiment. Another limitation of the DIC is illustrated here. If the subject goes out of the frame, you can't measure the displacement.
So we'd like to talk about some uncertainty that can happen using the DIC. First, if the condition change too much when the data it is collected, that can be a problem. In laboratory, it's not really a concern because you control all the factors. But if you want to use the DIC outside, on real structure, real building, if the light intensity or the meteorological condition change too much, it can add some uncertainty.
The number of pixels of your camera is really important as well. A better camera will get a better precision. If you get a higher number of pixels, you're gonna have a better resolution.
That's true. Finally, this method can be really useful because it's not intrusive. If we compare it to other measurement tools like the strain gauge, we can use the DIC and not be on the thing we measure. It can be useful when we want to measure displacement in extreme conditions.
In fact, when you use a strain gauge on the thing you want to measure the strain, it's gonna affect the specimen because the strain gauge, even if it's really small, has a resistance. It's gonna extend, so it's gonna participate to the resistive force, to the tensile stress that is applied on the specimen.
So let's talk about the DIC application. One of the first applications of the DIC is to measure thermal expansion. So the DIC can measure the difference in size of a tool when put under heat. The DIC is a non-intrusive measurement tool, so it's also really good to measure displacement in extreme conditions compared to the strain gauge.
Finally, one of the coolest applications of the DIC that we found was in Yosemite National Park in California in the US. There, they surveyed the cliffs of certain mountains to prevent rockfall. They used DIC to get a digital representation of the mountain and follow big movements of rock inside of the cliffs. Thank you for following, and this is the end of the presentation.